Hi. In previous lecture, we explained discrete time Fourier transform. And we said that the discrete time Fourier transform, it's used to perform the frequency analysis of discrete time signal. So if you have a discrete time signal like x of n equal 1, 2, 2, 1, and you want to express x of n and its frequency component, which is in frequency domain, we used to write like x capital of omega, whereas omega is the frequency. All right. And we said that there's something called frequency spectrum, and we divided frequency spectrum into magnitude and phase. Let's just have one example of one of the magnitude spectrum. They will tell you about the components, the frequency components of the signal after you use a discrete time Fourier transform. X-axis will be omega, and y-axis will be the magnitude of the spectrum. So if you see here in the graph that the magnitude spectrum of the signal, it's a continuous function of omega. All right. And if you are using the components, these components, and it's a continuous function, and you are using digital computer or digital signal processor, so you got to convert this into discrete in discrete form. So that's why you are going to use discrete Fourier transform. So discrete Fourier transform, it will transform this signal, this discrete time signal or the sequence, into discrete expression of the frequency spectrum. So how can we do that? There is an equation, and I know that you may think it's really hard, but it's not hard. But first, before applying this formula to find DFT, let's understand each component. That's xn. That's our digital discrete time signal. All right, that's discrete time signal, like this one. And you want to convert it to x of k. What does mean x of k? That's the frequency component. You will have, for example, x when k equals 0, you have x0. And when k equals 1, you have x1. What's x0? It's the average value, or the DC component. x1, this is the component that of the fundamental frequency. All right. x2, that's the component of the second harmonic. What does mean second harmonic? It means its frequency is double the frequency of the fundamental component. x3, that would be the component that its frequency 3 times the fundamental component. By the way, this is a fundamental component, all right? 3 means the 3 times the frequency of this component. So this one, its frequency 3 times this one, and so on. You can go whatever, but you got to know that the discrete Fourier transform, it's applied when the signal has a finite length, like 4, 5, 6, 7, limited. All right. And when it's converted to the frequency spectrum, which is x capital K, x0, x1, 2, 3, it's also converted to finite frequency spectrum. It's not from negative infinity to positive infinity. No, it is limited. All right. And by the way, the same number, for example, if you have in this example, we have x of n has 1, 2, 3, 4. It has 4 samples, right? 4 elements. The same thing, you will have 4 components here. You have x0, x1, x2, x3. So the number of the frequency component produced in this using this method will be equal to the number of the components of the discrete time signal. Okay, how can you do that? It's related by this function, w power kn. Well, wn itself is equal e power minus j 2 pi over n. N is the number of samples. All right. So that will be the base of the base that's used, and then you raise the power kn after that. There is a way that you can expand this summation, but I'm going to show you a simple method using matrices. All right. How we'll do that? It's very important how to find w first. So let's just see in this example. We have this signal or this sequence x of n equal 1, 2, 2, 2, 1, and it's plotted here. That's n, and that's the vertical, it's x of n. So here at 0, it means when n is equal 0, the signal is equal 1. When n is equal 1, the signal is equal 2. When n is equal 2, the signal is equal 2. When n is equal 3, the signal is equal 1. So you have 1, 2, 2, 1, and that's the way you express it in a vector form, and you underline the element corresponding to n equals 0. All right. So how many samples do you have? 1, 2, 3, 4. You have 4. And also you can get it from something else. You know, when you look at the last element corresponding to n equal 3, this is the last one. So the last element always equal n minus 1. So if you have n minus 1 equal 3, n is equal 4. So you got n equal 4. Right. So that's important. It's very important to find the number of samples so you can find Wn. All right. Let's see how we can find Wn. In this example, n equal 4. So W, I'm not going to write n here. It's equal E minus J 2 pi over n, and n in this case is equal 4. That will be equal E power minus J pi over 2. Well, you can use a scientific calculator in complex mode, or you can convert it to rectangular form. So you'll have cosine pi over 2 minus J sine pi over 2. I say minus because you have negative. All right. Cosine pi over 2 is equal 0 minus J sine pi over 2 is equal 1. So the answer will be minus J. So that's W. All right. So here's the what, right? Find minus J is W. We need to find, since you have n equal 4, so you got to find W power 1. We got to already W squared, W power 3, W power 4. Because we have n equal 4, you stop at 4. So how you find W2? W2 is equal, it means W squared, it means W times W, right? 1 W is equal minus J, you will see minus J times minus J. Negative times negative is equal positive 1, and J times J is equal negative 1. So the answer will be negative 1. Here you go. The same thing, I mean, let's just do it. W power 3, it means W squared times W. W squared, you got it, minus 1. And W by itself is equal minus J. So it'll be equal positive J, and so on. And W power 4, the same thing, you get it, plus 1. So you got the 4 elements. Remember, we got it from W power 1 up to W4. Why up to 4 only you stop? Because n is equal 4. All right. So remember, our goal. What's our goal? Our goal, this is given, the signal, discrete time signal with sequence given. All right. And we need to find the frequency component of this signal. So we're going to use this equation, and I will express it in matrix form. We have x of n, and we need to find W, and remember, W is power k times n. The power is kn. All right. I'm going to do something simple here. In this, that's your x of 0, x of 1, that's the given signal, the discrete time signal. We have up to x of 3, 4 elements. And it's required to find x0, x1, x2, x3. What are these elements? x0, x1, x2, x3 represent the frequency component. All right. This in matrices 4 by 4, 1, 2, 3, 4, 4 rows, 4 columns. You go there, and the first you put here ones in the first row and ones the first column. That's the first thing. And then you put W here, the rest of the matrix. You put 0, 1, 2, 3, and here you have 0, 1, 2, 3 outside. I'll tell you why. That like represent n, and this column represents k. Why I'm doing that? Because W is going to be raised to the power W here, power kn. So you multiply k by n. So I want to find the power here. So if you look, this is coming in the first or the second row, but the index 1, and that's 1. So if you go, you see like that, you'll find 1 times 1 is 1, you put 1 here. And this element, we multiply 1 times 2, it will be 2. And what you put here, 1 times 3, you get 3. Continue, let's just find this row. So what is the power of this W? That's 2 times 1 will be 2. 2 times 2, you'll put 4. 2 times 3, you put 6. The last row, 3 times 1 will be 3. 3 times 2, 6. 3 times 3 is 19. And now you may ask, okay, why you put 1s here in the first row? Simply because you can put W everywhere, actually. Let's say that you put W, for example, W here. You put W here. 0 times 3 will be 0. Anything power 0 is equal 1. That's why the first row 0, the first column 0, 0, W power 0 is equal 1 all the time. That's why. So just I made it simple. Well, now we have a problem. What's the problem? We have W1's okay, W squared, bar 3, bar 4, fine, but we have problem here. That's bar 6 and bar 9. We have up to bar 4, right? Remember, up to bar 4. Well, you can reduce it. Let me just show you. I wrote it in a nice way. So you don't have problem except only for this one, 3 elements, because you have only up to W4. It's simple. When you see it exceed 4, I mean, why? Just I don't want to memorize 4 the number, no n, because we have n equal 4. If you have n equal 5 or n equal 6, you will do the same thing, but choose the value of n. If you have 6 here, for example, that's W bar 6. You will divide 6 by 4. What you get? You get 1. 1 times 4 is equal 4. 4 from 6, remainder 2. So this one, you can change it, you just can put 2 instead, the remainder. And this is 2. 9. 9, you divide 9 by 4. It will be 2. 2 times 4 is equal 8. What's left is 1. So you can exchange 9 by 1. So that's 6 will be 2. And W power 9 will be 1. And the rest will be the same. So the first row, you have W power 1, 2, 3, 2, 4. Second one, 2, 4, 2. Let's just here you go. 1, 2, 3, 1, 2, 3. 2, 4, 2, 2, 4, 2. 3, 2, 1, 3, 2, 1. So after the reduction of power, I got this matrix. Well, now it's easy because the all values of W squared, we got it here. Negative J, negative 1. So just substitute. Substitute by the values of W and W squared. Here you go. Once you get this matrices, then you just multiply using a scientific calculator or computer. That's your x of n, the signal. Discrete time signal or sequence. You multiply this by this, and you got the result here. I want you to understand what does mean the result. This is x0. And that's x1. As you see, it's complex value, right? x2, x3. So we'll say that x0, this is the DC component. The DC component, it means you have the signal has DC component equal to 6. If you wish, you can say that you have DC. If you talk about voltage, so you have like a battery of 6 voltage. That's x. x1, negative 1 minus J. It's the fundamental component. What's the meaning of fundamental component? To be like you have a sinusoidal or cosine wave, okay? That's equivalent minus 1 minus J. Now you tell me what is the amplitude and what is the shift, because it doesn't have to start from 0. Maybe it starts, from delayed or advanced. I don't know what's the angle here. So we're talking about the amplitude and about the phase shift. It's simple. To find the amplitude, you write x1. I'm talking now 1, it means fundamental component. x1 is equal negative 1 minus j. I just got it from the result here. So if you want to find the magnitude, it's easy. You get the real value negative 1 and you square it, right? Because if you talk about the real value, let me just write something. The real value of x1 is equal negative 1. And the imaginary part of x1, don't write minus j. No, find what's the number associated with j. It's negative 1. So you square the real part, negative 1 square plus negative 1 square, you got square root of 2. So the amplitude is square root of 2. What about the phase shift? All right. The phase shift, you just use tan, the angle. What's the angle? Theta. Right 1. Why 1? Because x1. The angle is tangent is the imaginary part over real part, negative 1 over negative 1. All right. And you got to be careful about that, because maybe when you cancel negative with negative cancel, you will get different. You will get 45, because negative 1 over negative 1 be 1, and the angle 45 has tangent equal 1. No, you got to know that. Yeah, if both are positive, you get 45 degree, because the tangent of 45 is equal 1. But you have negative both the real and the imaginary are negative. That's the real axis, and that's the imaginary axis. That's the positive. That's the positive, that's the negative real, and that's the negative imaginary. So if you have it now, you understand. You have negative 1 and real, and you have the imaginary part, the vertical negative 1. So when you go there, that will be the angle. And you measure the angle from horizontal line. So what is this angle? All right. So you have to be careful about that. If you extend this one, yeah, if you're talking about the corresponding positive, you know that's 45. This angle 45, but you are measuring from here, from this axis. So you will go the whole way like that. So how you calculate? Well, from this axis up to this line, it's 180 degrees, and this will be equal to 45. So you can say that the angle theta 1 is equal 180 plus 45. 225. All right. Another way you can measure from the other direction. That's 90, negative 90, because when you are moving in this direction with clockwise direction be negative, and this is negative 45. So you can say it's equal negative 90, negative 45 will be equal negative 135. So we have the second answer. Both are right. That's positive 225 or negative 135. You are free to choose any one, but usually we're trying to choose something that less than 180 degrees. So you are going to do the process converting from rectangular form, x1 this rectangular form, to polar form. What's polar form? Instead of writing x1 equal negative 1 negative j, the magnitude is equal square root of 2, and the angle is, let's say, negative 135 degree. So that's the magnitude and that's the angle. You do that for x1, x2, x3, x2, yalla, x2 is equal to 0. So the all magnitude, you make it in one graph, you call it magnitude spectrum. The all phases also in a separate diagram, and you plot the phase diagram. Let me show you the result. This is the magnitude x of k. Remember, you have 4 values. So that's that's k, by the way, not n. K, it represents the frequency component. So that's the average value that we got is equal to 6, if you remember. And that's the what we got, the one with square root of 2. All right, you can find it in decimal. And the angle here, negative 135. That's what we calculate together. You do the same thing for the all component. But remember, you have how many components? You have 4 components. All right? But that's not n, that's k. The x-axis k. What's k again? Is the index of the frequency. So what does mean 1? 1 means the fundamental frequency. So you might ask me, okay, what is the frequency? What's the fundamental frequency? Omega, you have omega 1, you have omega 2, you have omega 3. So how can you find omega 1? Well, Let's just go there. I'm taking you here to this expression, all right? When you look at this one, look at the expression and the number of samples, all right? So you will say that the sample you took n is equal 4. In this case, omega is equal to what? It's equal to 2 pi over n. 2 pi over 4. Pi over 2. So that's the omega. That's omega what? That's omega 1. The fundamental frequency has frequency pi over 2. All right? So I wrote here omega 1 small, but because we are using this for the continuous, I'm going to change it to omega 1, omega 2, omega 3. If you ask me what's omega 0, I'm telling you the DC doesn't have frequency, right? It's 0 frequency, the DC, that is equal to 6 here. And the frequency 0. Omega 1, K1, it means corresponding to omega 1, which is pi over 2. Omega 2, you multiply by 2, and so on. So that's the magnitude spectrum, x of k against k, and that's the phase, theta k, and for each component. So this is the spectrum analysis for the signal that we have. Well, if you want to get the inverse, if xk is given, if you know the frequency component and you want to find the signal itself, sometimes you need it in the application, so just use the inverse of matrix. So x of n is equal to the inverse of the same matrix we got, but get its inverse, all right? And then multiply x of k, you get x, you get the original signal back, and you could check, you should get the same signal. I'm using the what using example we just explained now. So it's very simple and easy using this matrices by A, and as I said, it's important to calculate W, and from W you make this matrix, and you can calculate whatever like. I hope that was helpful, and it's better to also